I'm Fengchun from Dimsa. Today I'm going to talk about data, note and data, and I will introduce a new method called note data analysis. So here is the contents of my talk. So first, sorry. So first, let's give a quick review on knot theory. So we know an link is an embedding of disjoint union of n circles into the space. In particular, one link is called a node. Now, n link has n components which are totally entangled each other, and each component is a node which tied individually. A link is usually presented by a link diagram in the plane. Something like this. So these are all link diagrams. With a two link, sorry. So in usual, when we say a node, we mean a node or a link, and we don't distinguish a node between its equivalence class. So among all the diagrams of a node K, the number of crossing points on it with the least crossing points is called the crossing number, and it is denoted by CK. It's clear the crossing number of a node, trefoil, so this one trefoil, and the figure 8 node are 0, 3, or 4, respectively. There are three kinds of red-master moves on a node diagram shown in this picture. So type 1 is just from twist to untwist, or Wesley. Type 2, Type 2 move is just poke or unpoke, like this. And the third type is slide one string to pass a crossing of the other strings, like this. We call this the three fundamental red-master moves. So it is a theorem of red-master which says two links are equivalent if and only if for any diagram D of L and D prime of L prime, D can be deformed into D prime by a sequence of finite number of R moves. So here is an example. The red-master theorem plays an essential role in classifying knots and links up to equivalence. Here are some classes of knots. First, prime knots and composite knots. I don't explain the definition instead here. Torus knots, so which can be embedded in a standard unknotted torus in the space. And the third one is alternate nodes, like this one. So going along the direction on the node component. So under pass, in this way. This is called alternate nodes. The classification of knots up to equivalence is a fundamental problem in knot theory. So, given any two knots, how do we determine whether they are equivalent? For example, how can we prove the N knot and the trefoil knot are the same knot or not? You may try to use R moves to check if they are equivalent. And you will find that you cannot succeed after trying many times. But this doesn't imply they are not equivalent. Maybe you tried not enough long, or you tried in a wrong way. In fact, they are really distinct knots. They are not equivalent. So no matter how long you try and in what way you try, you will never succeed. So usually in knot theory, we use knot invariants to distinguish knots, the links. So a property P of K is called an invariant if all the knots equivalent to K have the property P. For an n-link L, both the components number n and the cross number CL are the invariants of L. So here are some simple applications. So for the n-link L1 and m-link L2, so if n and m are not equal, then they are not equivalent. If the cross number are not the same, then they are not equivalent. But if they have the same cross number, this doesn't imply they are equivalent. So to check a property P of a link L is invariant. So one only need to check the property P is kept under the three kinds of Rademacher moves. The main task of knot theory is to find out invariants which have strong abilities to distinguish knots and are easier to calculate. So in knot theory, we usually use this symbol, Ci or Cij, to denote a prime node. So here's the, So here's the table. So C is the cross number. So if no super index, so it means not. I'm not. So the I means the order in the list. So if it's a link, so J is the components of the links. So here is some nodes and the links, simple ones. Now we introduce some elementary invariants. So the first is tricolorability. So this is a very elementary invariant of knots. Use the tricolorability, we can distinguish the trefoil and the knot, the trivial two components link and the half link. Another invariant is chirality. A knot is chiral if it is not equivalent to its mirror image. K is a chiral if K is not a chiral. So trefoil knot is chiral. So this one and its image, this one are not equivalent. But the figure 8 node is a chiral. We can use some R moves to check. These are equivalent. But this one is the image of this one. The next invariant is a knotting number. A cross change in the diagram D is shown like this. So just exchange the outgoing arc and the undergoing arc, change the position. Set mk is the set of the integers. Here m by m times crossing change on a diagram D of k, now n naught diagram is obtained. This is the mk, and set uk, the minimum number in mk. We call uk the unnoted number of k. Here is some examples. That unnoted number 1 nodes. We can check the unnoted number is also not invariant. The next invariant is called link number. For oriented two link L and crossing C of L1 and L2, we assign +1 or -1 accordingly as shown. This intersection we call the positive, and in this way we call the negative. We call it the sign of the crossing C, denoted by this. The link number of L is defined the half of the sum of all the signs. For the oriented link J, the link number Lj can be defined in a similar way. So this is defined for two components. We can similarly define more for more components. And we can check Lj is also invariant. So use this link number, we can distinguish these two oriented half link. So the red component has the same orientation, and the blue one has opposite orientation. But they are not equivalent by the link number. Now we will review some historical fact. Not invariant can be numerical, such as crossing, or link numbers, polynomials, such as Alexander polynomial, Jules polynomial, Kaufman polynomial, and so on. And some more algebraically sophisticated, such as link homology theories. The study of knots began in the 19th century by Gauss, who first defined the link integral. In fact, it's the link number of oriented links. In 1885, Tait created the first knot table with up to 10 crossings. And since then, the knot theory became part of topology. From the early of the 20th century to the late 1960s, The knot group and the Alexander polynomial had been the main approach to the knot theory. A series breakthroughs have been made since 1970s. In the late 1970s, Thurston introduced the hyperbolic geometry into the study of knots, enabling the use of the geometry to define new powerful knot invariants, such as volume of knots. By the discovery of Jun's polynomials and the subsequent contributions from Witten, Conservich, and others, quantum polynomial invariants, Vassiliev invariants, and Havanov invariants of knots were successively discovered. But nowadays, there are much more invariants of knots. So these are only the tip of the iceberg of the modern knot theory. So here's the table. So number of knots link up to 22 crossings. So you can see for so one component is knot. So this is for the alternate link knots. So much bigger. So from the knot table, we see that the number of distinct knots increase exponentially with crossing numbers, which imply the knots themselves are bigger data. We will note as big data is a new area to study knots, in which advanced big data visualization techniques, dimension reduction, and machine learning methods are used. But in my talk, in the following, I will only focus on some applications of knot theory in data science, in particular in molecular biology. So we come to the second part of the talk. Noting and linking are very common topological features, not only in realistic world, but also at the molecular level. Molecular knots are widely found in DNA, proteins, and the synthetic chemical molecules. So nature knots usually plays a significant role in the structural, dynamic, and or functional properties of the biological and chemical systems. So here, by surgery, we're showing the cutting section, and so many knots we have found. The discovery of double helix structure of DNA was primarily made by Watson and Crick in 1953. Based on their model, DNA is a double-stranded molecule composed of two polarized linear strands which run in antiparallel directions and wind around an essential common non-linear axis. So in the middle is the axis. So double helix DNA can also be modeled as a supercoil, a ribbon, or a biot. The DNA of most bacteria and viruses is circular. So totally, in some way, can be regarded as knot links lie in plane. If no twist and nothing happens in the DNA, it is called a relaxed DNA. The vast majority of biological or synthetic polymers are open chains, not closed. But how we define the notice on the open chains? We define it this way. The open chain is often regarded as an open curve. It is noted if it doesn't disentangle after being pulled from both the ends to an infinity point, like this one. So this is a open chains or open curves. So we put the two ends of the curve to the point infinity and to join it together. So in this we get a node. We can also define the linked chains in a similar way. So far, there are over 750 noted proteins have been discovered within the protein data bank. And about 1% of all entries. This 750 is only about 1% of all entries. So we can find DNA the simple nodes or links, and as well as more complicated nodes and links we can find in the noted DNA structures. The long floating strands of DNA in the cell nucleus are usually packed in a twisted and tangled way, so that they become more tight, allowing for more efficient storage. So in recent decades, scientists have much studied on noting phenomenon in DNA, polymers, and synthetic molecules. The purpose is to reveal their topological novelties and puzzling folding mechanisms. Knot theory can be used to understand how nodes are formed in the molecule and what the properties of knotted one differ from the unknotted ones. There are some enzymes. We call the also another name is topoisomerase. So it's hard to pronounce. So I simply call it topoi for short, which catalyze both noting and unnoting DNA. So the action of topoids include three kinds. So one is cutting the DNA chain open at one place, and then move one part of the chain relatively to another, and finally resealing the two ends of the cut chain to form a closed system again. So when some critical process occurs in the DNA, supercoding, noting, and linking have to be relaxed by some topoids. There are mainly two kinds of such topoids, type 1 and type 2. type 1, just one string is cut and glue. And the type 2, so the two strings has been cut. But the glue may be in different way. So this is a way, so cut and glue. And this one, so cut and reglue in another way. So the process is very similar to what happens locally in node or link diagrams. Not in a single strand and double strand DNA chains were first discovered in 1966 and 1998, respectively. So, not very long. Since then, various noted structures formed in nicked or circular duplex DNA modular have been identified. And artificial DNA, RNA, and protein nodes have been successfully synthesized. So here is a table. So this is not the updated data. So now we see some applications of knot theory in molecular biology. So cellular process occur usually in relaxed state. So cells have mechanism to resolve the entanglements. So a knot number is widely used to estimate the number of times to untangle DNA. It provides insights into the efficiency and the mechanism of topology actions in cells and helps to analyze how they work and how they affect DNA structure and function. So let's see the second application. So chirality. The molecule of lemon is chiral. So the left-hand one has harsh lemon scent, while the right one has a more pleasing orange scent. So very different. The molecule of the drug thalidomide is chiral. It was once given to pregnant women to avoid morning sickness. Besides reducing the sickness, it also caused some kinds of birth defect. Later, it was found that the left one was making the mother feeling better, and the right one was causing damage to the fetus. So the characters, left hand, and another in the image is right hand. No half. No, depends on the some individual thing. Not the same number. So therefore, if a drug is known to be chiral, the pharma company needs to try to make just the preferred form in order to minimize the side effect and to maximize the effectiveness. It is usually costing, since the most methods of molecular synthesis don't distinguish between different casualties. In most cases, the wrong casualty produces the negative effect on human body. So now, so we come to the third part. We are now in the era of big data, so from weather report to the space exploration. Big data is everywhere. We can see every day. Big data is usually complicated, so that the traditional data analysis methods often doesn't work properly in finding the connection between points in data. In big data, there are often structural properties that remain unchanged under the continuous transformation, which are called the shape characteristic of data. In recent decades, topological data analysis, simply TDA, has been developed rapidly. It is a method to find the shape characteristic of data and widely applied across various fields, such as biology, medicine, and materials sciences. Although TDA has emerged as a powerful algebraic topology approach in data science, knot theory has less been involved in due to the lack of localization and coordinations. To address these challenges, we introduce a multiple-scale Gauss-link integer, a new effective data analysis tool. So next we introduce briefly the GMLI. Knot theory mainly concerns the equivalent class of knots. Knot invariants play an essential role in classification of knots. However, a knot can be deformed in a lot of ways. They are regarded as the same class, unchanged, before and after deformation. So knot theory is insensitive to local deformation. On the other hand, protein structure depends heavily on not only the total property, but also the local information. In molecular biology, individual knotted chains are more important. Protein structure analysis is sensitive to local deformation. So even a locally small deformation may cause changes in protein structure, affecting the expression of protein function. Next we come to the structure of proteins. Totally, there are about 4 kinds of four level of structure for protein. So the first primary structure, it is a linear amino acid sequence that makes up the P chain of protein, something like this. And the second structure is a locally stable structure, mainly including the alpha helix, like this, and the beta sheet, like this. And the other 2 structures will not be involved here, so we omitted to explain. So each P chain of a protein can be regarded as a linear graph whose vertex set consists of all the C alpha items. So the red one here. And the edge set consists of all edge connecting adjacent C alpha items. This is a P chain. All the P chains in a protein could be noted and linked totally and folded locally, such as alpha helix or beta sheath. So now we introduce the Gauss linking integral. So for given two curves, which could be open or closed, they are disjoint in the space and parameterized as gamma 1 and gamma 2. The Gauss linking integral of I1 and I2 is defined in this formula. This is first introduced by Gauss. Note the Gauss linking integral is the average of half of the algebraic sum of crossing between I1 and I2 in any possible projective direction. So it is categorized the degree of interlinking between the two curves. Here is the theorem. So for a two link, the Gauss link integrals is the link number of J. So we use the same notation as link number. If at least one of the curve is open, then the Gauss link integrals is the real number and continuous on the relative position of the curves. We will demonstrate our methods in a special case, so case of two curves. So we have 4 steps. So step 1, divide the two curves in some segments like this. The purpose of the segments is to increase the sensitivity of linkedness of the two curves to local deformations. Step 2 is to calculate the segmentation matrix G, so in which the item L PIQJ is the Gauss linking integrals of PI and QJ. So here is the theorem. The grand sum of the G equals to the Gauss linking integral of J. So all the atoms, the sum of all the atoms is just the Gauss linking integrals. Step 3, calculate the multi-scale segmentation matrix. So choose R, positive R, such that J is contained in the 3 ball of radius R. And we set d PIQJ to be the Euclidean distance of PI and QJ. And we use the distance characteristic function, chi, like this. Then the matrix of MGLI at scale, this scale is defined in this way. So it's also n times m matrix. And each atom here is the Gauss linking integrals of pi and qj are multiplied by the distance characteristic function. So this implies if the distance is not in the scale, then the Gauss linking integrals will be negative. Finally, so we obtain the multi-scale feature of the segment in this way. So for the scale, define the localized scale, the GLI, by this. So just take this just take the sum of the ith column items in the ith column, and this one is the sum of the jth row in the matrix. This scaled visualization is in fact a vector from MGLI for each curve segment U is defined in this way. So this is a feature of U. So here is the summary of the our method. So here are some remarks. MGLI is used to extract property GLI within scales. It provides an effective way to capture local interactions between segments in scale. The linking characteristics at various scales can be quantitatively captured. So cumulative integers across expanding scales can offer additional local structure insights. The global topological properties are finally recovered when a sufficiently large scale is reached. By using this method, we can locally and totally explore intervening, twisting, and folding of protein molecules, and gain a better understanding of the structure of the protein molecules. This method can be naturally be applied to link noise, open and closed curves, including a single curve, and other segmentable objects. It has been validated in quantitative protein flexibility analysis, drug toxicity evaluation, and some others. So next we see an application, protein flexibility analysis by using MGLI. Protein analysis. Proteins are flexible. The flexibility is often measured by so-called B factors, which serve as a prediction target in structural modeling. So high B factors means small atomic mobility, showing flexible or conformation changing parts. And the low B factors indicate rigid regions with less atomic motions. The B factor can be effectively detected by our methods. So here is some examples. The visualization of protein 1V70 B texture obtained from experiments MGLI and Gaussian network model. So this shows in this picture. And compare of the contain 1V70 B factors obtained from experiments MGI and GNM. So the picture shows the MGLI, the effect of MGLI is very good. And sorry, B so B factor. So here, so B factor silver. So I cannot explain it. Also, but only B factor silver. So if it is high, so it means more atomic mobility. Yes, some number. Some number. So it's some real number. Yes. Um, and the comparison of B factor predictions between our methods and other commonly used methods. So shows our methods outperformance are better than the usual. And this is another comparison. So this also show the MGLI performance much better. So I will so skip this part. So because of the time is running. So we can, in a similar way, we can use the Jones polynomial instead of the Gauss linking integrals to do a similar thing in data analysis. And here is the effects. So finally, the closing remark. Compare with the approach by previous knot theories, which mainly focus on the qualitativity of knots. The MGLI is both quantitative and qualitative strategy. By integration with machine learning or deep learning, the MGLI significantly outperforms other methods across various benchmark problems. The successful attempt to transform the invariance of knots into applicable quantitative features analysis. So initiates the knots data analysis, making it possible to apply more knot invariants, such as polynomial, Fourier homology, homology, as well as the GIYY theory, to many fields related to the knot data and achieve more accurate and efficient data analysis. It's possible. And to explore knot invariance from the local information might feed back to the study of knot theory as well as the study of knot data. I'll stop here. Thanks for your attention.
Thank you very much. Are there any questions? Thank you for the talk. So I want to ask. So the method of this MGLI computes the data of one protein or a link of protein. So in practice, the protein comes. I guess we get a bunch of protein, and if we try to analyze them together, does this method of MGLI give you some consequence which is useful, or do you need other method to analyze it? I feel like if one just analyze one protein, it's kind of far from the application, right? It's just about the structure of one protein. But in practice, maybe we need to dealing with a large amount of protein or data together to study the more microwave effects of the proteins. Yeah, that's my question.
So what's the key point of the question?
Oh,
So it's too long.
sorry, let me repeat. So it seems to me the
MGI1.
MGLI method you mentioned is the analysis of one protein or a link of protein. The structure, both local and global, is the quantitative version, right? So I'm asking, so in practice, in biology or chemistry, we will have a bunch of protein get together, right?
Yes.
And so one, so maybe they have similar structure topologically, but the local structure might be different from each other. And we want to analyze them together as a group of molecules. So then does this method of MGLI help to analysis a big group, or you need
works? So the link contains many components.
Pardon?
So the link can have many components.
Yeah, but in practice, I think we consider a link with a small number of components, right? As your example illustrated, you only consider a link with two components, right?
Yes.
And I mean, for example, if we are dealing with medicine or what, we have a tablet which contains a lot of maybe millions or hundreds millions of protein inside it, right?
Yes.
And so it's not practical to analysis each one of the protein in the tablet, right?
Yes.
So how do you
But biologists can separate to give a single one.
Oh, you mean you can extract maybe one
can separate from
a bunch of proteins and analyze one by one.
Not one by one. So one class.
One class.
Yes.
Okay. So even in one class, well, local structure might be different from each other, and as you said, it's sensitive to the local deformation, right?
Yeah.
And so how do you detect the different even in a class, the different local structure might affect the biological function?
That's the scale. The scale plays the role. So if the scale is small, so you can small local. And if you get large the scale, so you can find a more.
Yes.
Yeah.
Okay. So if we consider analyze it in a small scale, then we need a large computation.
Sure. So the amount of computation is large.
Okay. Do you have
very huge?
Analyze of the computability of the...
Sure. Yeah.
Okay.
That depends on the ability of the computer computing.
Okay. Yeah. Thank you.
Okay.
Thank you for a very nice talk. I just wanted to ask if you try to apply it for notorious or link curls.
Sorry.
Okay, so I want to ask if you try to apply this method to say notorious.
Sure. Yes.
You will try.
Yes, but we will not started. Just,
Oh.
oh yeah. So so for some so the funding studied.
Okay.
Yeah. So
Any more questions?
It is more like a comment to the previous question. As far as I understand your question, the question is about something like stability theorem. Like if you have small changes in your original protein, um, is your invariant stable under small changes?
yes. Yes, stable. So in fact, it's a invariant. So if you change the coordinates of the curves, and so if it is so maybe by homotopy, it is unchanged.
I see.
Yes.
Thank you.
Any more questions?
Gauss linking members consist of two sections. One section measures the racing member, and another section measures the twisting number, right? So I mean, this has is these two members has the same sense in this method, or has a different sense?
Sorry, so I don't understand what you mean. What do you say?
Yeah, I mean the Gauss linking member
Mhm.
have two sections.
Yes.
The one section is to measure the racing member. I mean the self maybe the self member,
Mhm.
and the other member is measure the twisting member, right?
Yes.
I mean these two members have the I mean have the same effect in this in the protein, or has different. Because the question is about if you change something locally, it may I mean it may change the one section or the another section. I mean it may have different effect.
Yeah.
That's my question.
So totally linked number is topological invariance, but you mentioned the other two, so may not invariance. But so for closed curves, so they are invariant, but for open curves, it may be changed.
Yeah, yes. I mean, so this question is about if you change something locally, you may you can maybe you just change the racing member, and you just not change the twisting member.
Yeah.
Yeah, as these things, so it don't have some effect in this method, right? It's stability with this thing. I think it's you.
But then, yeah, it's invariant, so the total is unchanged.
Totally is invariant.
Yeah,
Yeah,
yeah.
but I mean, in locally it will change.
Locally
some-
may be changed.
Oh, I see. Thank you.
Any more questions? If there are no more questions, let's thank Professor Lei again.